Hi guys, welcome to another Under the Hood of. Today we'll be taking a look under the hood of Git. So for many years, Git has been the source control management or the version control of choice. It offers many features which alternatives such as CVS did not, and combined with the GitHub website, created this CI pipeline which many teams build practices around now. When I began reading about the mechanics of Git, it was obvious that it's a combination of many different techniques, all of which produce this replicated version file system which is known as Git. So a couple of examples: there's linked list, there's a file system object database, there's hashing, there's several different types of hashing, and differential encoding. And we'll be taking a look at all of those later on. So I decided to create a mini working version with some of the core version control features. And thankfully, there are many helpful books which break down how things work. So I've attempted to strip the internals down to its bare minimum. So today we're going to be focusing on repositories, working directories, staging, committing, and status checks. So there's a lot that I've left out, such as pack files, deltas, branches, tags, merging, and comparing the stage chunks, also known as diffing. I may do a follow-up post. So this talk will be broken down into the following parts. We've got part A, which is going to be the overview of Git, which looks at the workflow, the object model, the components, and then part B, which is building our own Git, the Git code, and then how I tested it. And then part C is just what ours does not do, which the real Git does. So let's start with part A, an overview of Git. So Git is described as a distributed version control system which tracks changes in any set of files. It was initially released 15 years ago, in 2005, and has grown in functionality and popularity massively since then, as any developer who uses GitHub knows, or any alternative, the GitLab or Bitbucket, has become a staple of the world of software as a best practice. I'm not going through how it is used, but the basic workflow can be summarized by the following 5 steps. We initialize a new Git repository. A file change is made locally and saved. The file is added to staging. The file in the staging area are committed. Finally, the commit is pushed to a remote repository, put in the latest before doing so. So we will break down each step, but before we do, we need to review the mechanisms at the core of Git, which is the object model. So the object model is essentially an incredibly efficient version file system with replication. Each file in the repository exists in the file system and in the object database, as you can see from file A there. The object database is a hash of the contents. A hash is an object, and there are 4 types in total, but today we're going to be looking at these 3, and that does include tags. So today we're going to be looking at blob, which is a sequence of bytes. A blob in Git will contain the exact same data as a file, it's just that the blob is stored in the Git object database, so it's basically the file contents. And there's a tree, which corresponds to Unix directory entries. They can contain blobs or subtrees, or subdirectory. The commit tree has the entire project in blob and trees at the time of the commit. So you can recreate the entire project from that tree, always from the root directory, even if a subdirectory file is being updated in the commit. And then there's commits, where there's a single tree ID and the commits preceding it. So each tree node, commit, and file have their own unique 40-character long SHA-1 representation. The file name is a hash of the contents. If the contents change, so does the hash. Each time it changes, a new entry or hash is added, but it keeps the old ones. Inside a Git repository, they're all found under .git/objects folder, and you can see all of them in there. And this is actually my favorite image to describe the structure. Got the commit on the left, the trees in the middle, and on the right we've got the blobs with the content. So within the object model, the file name is a 2-way SHA-1 encoding of the contents, the hash. Git prefixes any blob objects with blob, the word blob, followed by the length as a human-readable integer, followed by a null character, and you can see the example there. We've got the S, and we're printing it, doing a hash object, which is equivalent to the code below it, where we're just blob and then doing a SHA-1 sum. The object file contents are suppressed via the deflate Z algorithm. It's less human readable or file name friendly, but a more efficient encoding. So you can already see just in this slide, there's two different forms of hashing going on, and they're used for different things. It's a file name and the actual contents. So I'll be covering the components we'll be building in our working versions later. So the working directory is the current system folder with the Git repository in, also known as the working tree. There's the head, which is a file holding the ref to the current working branch. It's basically the last checked out workspace. It holds a reference to the parent commit, which is usually the last checked branch that's checked out. Also, it's found in the .git/head file, and you can see an example of its contents here. And this one is actually pointing to master, and you can see master is pointing to a Git ID, a commit ID. Branches. Branch is actually just a named pointer to a specific snapshot. When it's checked out, three things happen. It moves the head pointer to point to the feature ref, or the branch. It moves all the content from the current branch repository into the index file, so it's easy to track changes. And then number three, it makes working with the directory match the content of the commit pointer to it, and it uses the tree and the blob objects to update the working directory contents. Tags are an alias for a commit ID. The head will point to the latest or predefined, and so for example, there's git refs head tags tag name, so the head would point to that tag. Repository, which is a Git project stored on the disk, i.e. not in memory. It's essentially a collection of objects. There's staging, which is the area between the working directory and the repository, and all changes in staging will be in the next commit. We've got the index file, which is it's a binary file. It doesn't hold objects like blobs and trees. It stores information about the files in the repository. It's a virtual working tree state. The index file is located at /index, and you can see the status of the index file if you run this command, git ls file and stage. Information stored. For each file, it stores the time of the last update, the name of the file version in the working directory, the file version in the index, and the file version in the repository. And file versions are marked with checksums. This is a SHA-1 hash of stat, the function stat. It's not a hash of the content, and this is more efficient. So you can see here, this is the third type of hashing that's been going on. Continuing on with the index file, for refreshing, it's updated when you check out a branch or the working directory is updated, and it's running in the background automatically. And then finally, the actual hashing itself, it uses a file system stat to get the file's information, to check quickly if the working tree file content has changed from the version recorded in the index file. It checks the file modification time, which is under the stmtime property. The refresh literally calls stat for all files. So now on to part B, where we're going to be building our mini working version of Git. The code consists of 4 files, one for each command, plus a utility file. So we'll start with the init. You can see part 1. So what I've done is I've put a comment for a number, and the number is where I'll be referencing. So if we look at number 1 on the right, commented up, grabs all the files from the current working directory. 2 lines down, number 2, build the index file using the stat SHA-1 hash from each file. And then all the way towards the bottom, number 3 is write a repository folder under the .repo. And then we've got 4, which is inside the repository, we're going to write a head file and the objects folder. Onto the status. For number 1, we grab the index file. A bit below that, for number 2, for each item in the index data, we are going to A, grab the file's stat SHA-1 hash. Then B, if it doesn't match the current working directory, stored the hash of the file, flag as changed, not staged. C, a bit further down, it does not match the above, but doesn't match the stage. We're going to flag it as not staged. D, just below that, it does not match stage. It does match stage, but not the repository. We're going to flag it as not committed. 3, a bit way down, we're going to update our index file. 4, we output the local changes that are not staged, and 5, we output the staged changes that are not committed. Onto the add. starting on the left, number 1, we explicitly give the files, for example, 1 or with a folder 2, 3. For each file, to move on to number 2 now, where the blob hash is, for each file, we get the contents in SHA-1 and use that for the directory name and the file name. Now number 3, all the way down to blob compressed, we get the deflated value and use that for the content. And number 4, further towards the bottom, we get the SHA-1 value for the file stat. Now we look on the right. Number 5, we're going to update the index. Number 5a, if the file was not touched, just proxy the values. 5b, if the file was touched, we're going to update staging for the file. And finally, number 6, right at the bottom on the right, we're going to override the old index data with the new index data. On to the commit. So number 1, we grab the files to commit. Number 2, a bit further down, we build the tree for the files in staging or the committed. We exclude the working directory. You can see the code for this actually on the right. It's this build tree utility function. What that actually does is that returns an array of the directory name and the files, which is the children, ordered by bottom up. Back on the left now, number 3, we're going to iterate the items root tree into a flattened array of trees. And the way that this goes is with 3a, if it's a tree, we create the tree for children. With 3b, then we're going to add the children to the flattened tree. And then finally 3c, if it's not a tree, we push with the previous tree. Commit continued, because it is a big file. So for number 4, we create the tree object for the root. Number 5, we then create a commit object using a parent commit if it exists and the tree hash. For number 6, from the commit object, we're going to get the commit hash. This is the bottom on the left. Now on the right, number 7, we update the index file. Number 7a, if the staging hash does not match the repository hash, then we update it. An existing file has been updated. And then finally, number 8, we update the head with the latest commit. So I've included the helper file, but I'm not going to walk through all of it. So for anyone interested, I'd recommend looking in the repository link at the end. The names are pretty self-explanatory. Basically, the SHA-1 hashes are done with crypto. I use process.cwd for the current working directory. I read the file contents with fs, as you imagine on Node, and deflate compressors with zlib. The largest utility methods are these two. There's create tree object and create commit object, both of which do very similar things. So they process the given contents into a hash. They then compress the given contents. They then write the compressed contents to the respective directory and file. And the way they do it is that the first 2 characters of the hash become the directory and the rest becomes the file name, as is you would see in Git. So I wrote a small project to test this version control. There were 3 files, each with a line of text, 2 of which are inside of a folder. You can see them there. There's the 1.txt, then a folder of 2, and then inside there is 3.txt and 4.txt. In the actual repository, these will find the scripts are found inside of bin, and the working directory or the application is found in the source folder. And that's in the actual repository I'll link in a moment. So then I wrote some integration tests, and this is the index.integration.spec file that you can find in the repository. To help keep track of what happens to our repository for a given command, the steps and the results are here. So step 1, repo.init, we create the index with the current working directory file's stat hash. Then number 2, the status, we flag 3 new local changes that are not staged, those from above. Then repo add 1 and 2.3 should create the blob objects inside 2 character long directories with the content compressed, should update the index and move items to staged. And there's a status, which will flag that 1 new local changes are not staged and 2 changes are not committed. I then manually update the 1.txt file and then do another status, number 6, similar to the previous one, except it now flags that 1.txt has locally changed. Number 7, we add 1.txt again, so we're re-adding the uploaded file. one.txt should update the blob object. Let me run status again. The re-added file should now show with the old added file. Then we add the for.txt and add for.txt, so the 2 items in the tree object. There are now 2 items in the tree object. And then finally number 10, where we commit, and this creates a tree and a commit object and updates the head and the index. So check out the repository for the code and the parsing integration tests. So finally, what have we missed? As mentioned, there were many additional parts to the real Git version control system, which I omitted. Some of those are comparing the change chunks like diffing, pack files, deltas, branches, tags, and merging, which are all very important parts of Git. So that's it. Thanks very much for watching. I learned a huge amount about Git from this research, and I hope it was useful for you. You can find the repository for this code here, and check my site for more Under the Hoods coming soon. Thank you very much.